and Assalamu alaikum, guys. We are starting off with a new chapter that is electric field, and it's a small section. We will do two chapters in this section. One is the chapter of electric field, and the other one is capacitors. These are two interrelated chapters. First up, guys, you need to identify. There's a lot of similarity of this chapter with the chapter of gravitational field. You have field lines over there. The only major difference is that it's a bi-directional force. In gravitational field, it was only attractive force, but in electric field, it could be both attractive or repulsive force. So first thing is that what is an electric field? So it's a region space around a charged object so that it is able to exert attractive or repulsive forces onto another charges. And we represent electric field by means of field lines. And you did that back in AS level. You did a lot of electric field patterns back in AS level as well, where you make field lines from positive towards negative charge. If the field lines are close to each other, you'd say that the field is strong. If the field lines are away from each other, you'd say that the field is weak. So obviously that's sort of a measure of how strong or weak is the electric field. The directional field basically represents the direction of force on a positive charge. So if you have a field being represented, so you know that the direction of field would be the direction of force that any positive charge would experience being placed over here. And opposite to that would be the direction of force onto any negative charge. So that's like sort of the sign convention. If you put a positive charge, likewise over here, if you put a positive charge, it will experience force same as the direction of field. Whereas if you have a negative charge, it will experience force opposite. Sometimes you have field lines being represented as curves. So you draw a tangent and that tangent represents the direction of force on positive charge. Opposite of that would be direction of force on negative charge. So as I said, I mean, you've done the field patterns of point charges, you've done the field patterns of parallel plates as well in AS level. You need to sort of remember those. But somehow an important concept that would be added over here is a concept of charged metal sphere. It doesn't matter whether it's hollow or solid, but if you have a charged metal sphere, the first thing you need to understand is that if you provide charges to the metal sphere, and of course, if it is charged, it would be either positively charged or negatively charged. And if it is either positively or negatively charged, let's say you talk about it being positively charged. So it has excess positive charges, and all of those excess positive charges must be repelling each other. That leads to them being evenly distributed on the surface. And even if solid bhi hoga, to the charges are not going to be inside this way. They're going to be right on the surface, and they're going to be evenly spread throughout the surface. So, so what you need to identify is that, first of all, if there is a charged metal sphere, all the charges, be it positive or negative, are going to be spread throughout the surface of that metal sphere. The other thing you need to identify is that you would treat a charged sphere as a point charge. That is, you would treat a charge sphere as if like all of the charge is concentrated right at the center. There's only the entire charge is in the center, and it's all concentrated at the center. So you would not consider it as a sphere while doing your calculations. Even distances are going to be considered from the center of the sphere. The reason for that, or the justification for that, even examiner asks, why are you doing that? And you would say that because if you would extend the field lines, they seem to be either originating from or to the center. So that's why you'd consider all of the charge on the surface of the sphere to be concentrated at the center of the sphere. So this will be treated as a point charge. In case of positive charge, the field lines appear to be originating from the center. In case of a negative charge, field lines appear to be converging at the center. But all of this is going to be considered as point charge, be it positive, be it negative. Also, there's one more thing. The effect of it being a point charge is only experienced outside the sphere. Inside the sphere, there is no electric field, there is no electric force. What do I mean by that? Let's say I put a test charge. I put a proton or an electron anywhere here. that proton would experience the same force near the sphere as it would have experienced had it been a point charge right at the center. Whereas if you put a positive or negative charge over here, it will not experience any force at all. There is no field inside the sphere because the field lines inside the sphere would cancel each other out from the opposite ends. As it's going to be evenly spread out, so there would be field lines exerting from both directions and they will be canceling the effects of each other. So, and the main point is that if I put an electron over here, it will experience a force as it would experience a force had there been all of the charge concentrated at the center of the sphere. So it would be treated as a point charge. But if I put an electron anywhere inside the sphere, then it wouldn't experience any force as if there's no source of charge present. And that's because the field lines inside the sphere, be it positively charged sphere or negatively charged sphere, the field lines inside the sphere would be canceling each other out. Just like we have Newton's law of gravitation, we have Coulomb's law as well that is used to identify the force between 2 point charges. So my point charges के लिए ही ये formula applicable होता है, but even if it's a charge sphere would be treated as a point charge. And it is also an inverse square law, just like gravitational force, which says that the force between 2 point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between their centers. And that gives you a formula for the electrostatic force, which is QQ over R square. If you remove the proportionality sign, you get a constant of proportionality, which is a little weird one, 1/4 pi epsilon naught. But epsilon naught value is going to be given to you in exam. You can also simplify this thing 1/4 pi epsilon naught into another constant and call it K. And that value is 8.99 times 10 to the power 9, and that's also given in exam. You must be wondering, why are we given two different formulas? It's just like, basically, epsilon naught is an important quantity. That's a quantity which is called permittivity of free space. And you need to know that. This is called permittivity of free space. And basically, this is sort of a measure of how easily field lines can pass through air. So if you're using some other medium, you wouldn't use that. It's not part of your syllabus. But if you were using any other medium over here, then it gets multiplied by another epsilon that's called ER, that's called relative permittivity of that particular medium. That's not in our syllabus. But you need to know that the formula is written like this, where epsilon naught is called the permittivity of free space, and that has this particular value. If you would calculate yourself, because अगर आपको epsilon naught दिया हुआ है, अगर आप इसे calculator में put करेंगे 1/4 pi epsilon naught, तो आपके पास यही answer आएगा 8.9, which is a very easy value to remember as well. But the good thing is कि examiner doesn't even want you to remember this. ये भी examiner देता है. सिर्फ फर्क ये है कि जब आप quick calculations करना चाहते हैं, you prefer this form. Whereas if you're being ever asked to define it, then you have to use this form. ये form आपको definitions के लिए इस्तेमाल करनी पड़ेगी. कहीं पे भी अगर आप define कर रहे हैं that what is Coulomb's law. The law is very similar to, as I said, the Newton's law of gravitation. इसी तरीके से, and the entire sort of series of concepts would like sort of overlap with each other. Just like when we were doing gravitational field, and we did talk about Newton's law of gravitation, and then we talked about gravitational field strength as well. So gravitational field strength over there was defined as a force on a unit mass. Here, the origin of force is charge. So electric field strength would be defined as force on a unit positive test charge. So if you're looking for a force on a unit charge, then in place of small q, you're going to put 1. So that gives you a formula for electric field strength. So very similar formula with the other charge being equal to 1. You can, for calculation, you can also write it down as kq over r square. It's an inverse square relationship, so you can easily identify how the graph would look like. It has its sign conventions. Electric field strength could be calculated for positive charge or could be calculated for negative charge. Whatever you calculate, I mean, there is a meaning. A positive means away or outwards. and negative means towards or inwards. So if you're talking about the calculation of electric field strength, and once you do your calculation, तो वो electric field strength या तो away outwards आएगी, so that would be represented by a plus sign. So when you're calculating force, guys, even if you're calculating force, if you would put both positive, you'd get positive answer. Means outward repulsive force. If you put both minus, even then you would get positive answer. That means repulsive outward. But if you put one positive and one negative, you'd get a negative answer. That means inwards attractive. The same thing applies to the electric field strength. When you're calculating electric field strength, you do positive charge, you put a plus sign into it, and you get a positive answer, which means outwards away. Whereas if you put a negative sign, you'd get a negative answer, means inwards towards. And hence, that's how the graph is being represented as well. It's an inverse square relationship graph. So it's going to be asymptotic to y-axis and x-axis. X-axis over here represents the distance, how far away you observe the electric field strength. It carries both positive and negative signs. It wasn't happening in gravitational field. और अगर मैं यही इलेक्ट्रिक फील्ड स्ट्रेंथ ड्रॉ करना चाहता हूँ for charge sphere, so I should know कि पैटर्न यही होगा. It will follow an inverse square relationship, but it will only follow an inverse square relationship till you are outside the sphere. The moment you enter the sphere, the electric field vanishes. There's no electric field, there's no electric force inside the charge sphere.